Good afternoon, everyone. My name is Aveen Dayal. I'm a PhD scholar at IIT Hyderabad, and I think we can begin with the session. And yeah, let me just share my screen, and we can begin with the session. Yeah. So this will be the final session for the course Deep Learning for Computer Vision, taught by Professor Vinny. And in today's session, the goal is to basically revise all the concepts that throughout the entire course we've been talking about. So I'll basically be covering from each week a few concepts, and so obviously this won't be an exhaustive set um, given the time limit. So I'll try to cover as much and as many topics as possible. And yeah, so let's get started. So in week one, in the beginning of the course, the first thing we talked about was histogram equalization. So in histogram equalization, what we wanted to do was the goal was we had any distribution like this, a histogram of an image like this, and as you can see, the x-axis is the intensity, and the y is the basically the count of each pixel value, how many times it is repeated. So usually you can imagine the x-axis to be values, integer values between 0 to 255, and each pixel value will repeat some n number of times, and that count will be on the y-axis, this red color plots. So in any typical image, what we experience is that sorry. So in any typical image, what we experience is that basically the histogram of that particular image won't usually be equally distributed. Sometimes there are certain pixel values which are high, sometimes there are certain pixel values which have no count at all, and some which have low count. So in histogram equalization, what we try to do is we want to go from a distribution like this to a distribution which is more equal, which is more uniform. So in this case, we are trying to basically fill out the pixel values which have not been present. So we make picture look more smooth. And what do you mean by that is this particular image. So as you can see in the original image, since only certain pixels are repeated, the histogram which we form is not very equal, is not uniform. And there are only certain peaks at certain pixel values. And most of the other pixel values, it's almost zero. But when we do the histogram equalization, we now give a more clear look, a more deep, like intense image, because we are forcing the image to have all types of pixel values, so we can see the gradients, basically the different variations or different depths or edges which are present in the image, because now we are forcing him to have different pixel values. So the graph which you get finally after histogram equalization is the one below. Obviously, this is not exactly uniform, but it's close to uniform than what the original image was. So this was the technique which we used in histogram equalization. So if you have any questions anywhere in between, so you can always post it in the chat, or you can unmute and ask. So yeah, yeah. And then after histogram equalization, we talked about filters, and one such linear filter was sharpening filter. So linear filters is nothing but you have a filter of 3 by 3 or 5 by 5, and this 3 by 3 or 5 by 5 filter, you apply it on the original image, which is like you can see an original image like this, which could be 224 or 224 or 512 comma 512. And what you do is you basically do a linear wise, element wise addition. So each this 5 by 5, you place it on a patch of this 3 by 3 on the input image, and each element you multiply and sum all those multiplied elements, and then you get an output value. You similarly then move one column to the right. If the stride is 1, you move one column to the right, and you keep on doing this until you complete all the pixel elements in this particular input image. So based on what type of a filter you use, so like in this case, we are using a filter like this. So the output what we get is more sharpened image, like you can see in the bottom. If you use different filters, you'll get different types of outputs. So if you will talk in the next class how you can use filters like Sobel detectors, which will only detect edges. In this example, since we use a filter like this, which is a Laplacian filter, which is used for identification to sharpen the image, we after doing the convolution or the applying this filter on the input image, you get the output as this. Similarly, there was another example of image thresholding. So things like where you want to create a step function type of an equation, like where if you have a certain pixel intensity greater than a certain threshold, like 100, you make it all 255, the pixel values, whereas otherwise you keep it all zero. So basically, what we want to do is a picture of Mona Lisa, like on the left side. We want the output to be something like this on the right side. So then the question was, can such operations be also be implemented as filter? The answer was yes. You can always create a function like you can create a filter like this with the same concept. You can always use the same logic over here and create a filter like this. And if you want to check whether a filter is linear or not, the important conditions which we had were these two conditions. Basically, if G is linear, then this condition should be satisfied. The G of A plus B is equals to G of A plus G of B. This basically the composition function. So if you take a look, yeah. So we checked for this particular thresholding operator. G is equal to 255 comma 0, 255 and 0. If you want to check if this is a linear filter, you basically check the linearity condition. And this is some example where if we had at one pixel location the value is 90 and the other pixel location the value is 20, then if you send that pixel a m comma n into the function g, you'll be 0 because this is less than 100. Even this is 0 because this is also less than 100. So as you can see, a plus b together is 110, whereas if you do individually g of a and g of b, you'll get 0. So since this is not equal, here we say it's not a non-linear field. So this particular thing, it can't be a non-linear filter. Sorry, my bad. It can't be a non-linear filter. So because this operation is not being satisfied, this particular condition is not being satisfied. So my error in previous what I said. So this particular image thresholding equation, this can't be implemented as a linear filter like this particular sharpening filter. And then other type of filters can be the Sobel operators. So as you can see, just a second. Yeah. So another operators are Sobel operators. These are usually used for edge detection algorithms. So for example, this particular uh, filter GX, this is used for detecting all the edges in the X direction, and GY is used to detect all the edges in the Y direction. Again, what we do is basically we take this particular filter, which is this 3 by 3 filter. We place it on the original input image, which is this 4 cross 4 image, and you can see the color, right? All the green color things over here will overlap with these green color things. The blue color things will overlap with these blue color things. And what we need to do is we multiply -1 into 100, minus 100, -2 into 100, minus 200. So and so do for all the 3 cross 3 elements. And then we add them up. And whatever will be the final value, that will be the output of doing the Sobel filter on this particular 3 by 3 patch. We then repeat it for all the other elements in that particular input image. So output will be over here. You'll get some 2 cross 2 output basically after you do the uh, Sobel operator on this particular input image. So what do we get basically with the Sobel operator is edges. So as you can see, when I do, yeah, sorry, yeah, as you can see, the Sobel operator over here, if you do Sobel operator Y, then mostly all the vertical edges are being detected. Sobel operator Y, mostly all the horizontal edges are being detected. Whereas Sobel operator X, mostly all the vertical edges are detected. So if you notice clearly, this is a horizontal edge which can be detected only in Sobel operator Y. And this horizontal edge is not being detected Whereas similarly, if you look at these curves of this particular object, right, this is more vertical rather than horizontal. So that's why this will be detected more in the Sobel X direction. So another example is when you combine both these, like a filter like G, where you combine both GX and GY, then in that case, then you'll get uh, more different types of edges, not just edges in the vertical or horizontal direction. So in a similar way, you can always keep on experimenting by increasing the magnitude values, by making the filter size bigger. What type of different operators, edge operators you can create, you can see. So by increasing magnitude values, you will be able to detect. Uh, by increasing the magnitude value, you'll be able to detect more sharper edges, more smaller edges, and similarly, if you also have to go from plus to minus, and if you don't go from plus to minus, then you won't be able to actually detect the edges. If you go only from +1 0 to +2, it won't really capture the edges. It should always be the gradient change. So if you look into the math behind it, it's a gradient change. So it should go from one positive direction to the negative direction, both for x and y. And if you increase the patch size also, uh, you won't be able to see smaller edges, you will be able to capture more bigger edges. So that you can always experiment with the filter size and so yeah, this is the this is the filter where you take the magnitude of gx square plus gy square whole under root. And in this case, as you can see, both horizontal and vertical are being detected. So this was the horizontal, this was the vertical, which we saw in the previous example, which were not being detected respectively. But now in this particular filter, both are being simultaneously detected. So you can always play around and identify better edge detectors. And then after edge detectors and all, we talked about SIFT algorithm. So the algorithm itself is a big topic. So I'll just give you an overview of the SIFT algorithm steps. And if you have any doubts, we can discuss further. So basically, what SIFT algorithm does is it basically identifies your important features of a particular image. It creates the image descriptors, you can say. So how it does in four steps. First is the scale space extrema detection, where you identify across different scales and different sizes, basically octaves and scales. You identify all the interesting points in your input image. Then after that, you you find out the difference between the simultaneous two scales to identify basically the Gaussian points. Basically, we identify the gradients. Basically, the difference of Gaussians basically give us the Laplacian. So we're identifying kind of like a gradients, you can say. And then we identify all the important and interesting points in that particular image. And then in step two, after we determine the location and scale of each of this interesting point we identified in the step one, as you can see in the below. And then in the step three, we now, after identifying the location and scale, we now want to estimate what is the orientation of that. So we basically use gradients over here to identify what are the orientation of those interesting key points which have been localized in step. And then after that, we write a descriptor. Now this descriptor is nothing but it's an information. It's, you can imagine like a dictionary containing all the information of that particular interesting key point. The information could be either your orientation, your location, etc. And like basically what is your shape or illumination and different kinds of information. Those all will be stored in this particular descriptor. So in this way, we are identifying all the key points, important key points with their own descriptors in a particular input image. So this was the SIFT algorithm, which we talked in, I think, week three. And then we went to a ransack algorithm. So after identifying your important, interesting points, now we want to do feature matching between two such images which have their own corresponding interesting or key points. So how do you do feature matching? We can use one algorithm which is very popular and famous. It is the ransack algorithm. So again, this is the template of the ransack algorithm. So what I mean by template is, so this is the algorithmic template. So most of the ransack algorithms is not just for feature matching. It can also be used in regression type of a problems, which we discussed. So I'll just give you an overview of this ransack algorithm. So what we try to do is we have our initial data X, and then we'll have another parameter called minimum number of samples we pick at each time to fit that particular model which we are trying to find. And then we have also score function which says ki, okay, how good is this particular parameters, model parameters, given this number of samples and the data is present. So that score value is basically determining if the current model parameters are good enough or not, or if it's not good, then we basically iterate and find another set of parameters. So that is the basic for loop what we do. So what we do is, in the first step, we pick some n samples from that entire data. We fit the model h with those n samples and compute the parameters theta. And once you compute the parameters theta with this particular h model, we now verify, basically we now find out what is the score. So you can have any scoring function, like any loss function. You can have MSE loss or L1 norm loss or any loss basically, and you find out your score. After you find out your score, then you can see if this particular score is better than all the scores you had up till now. And if yes, then that will be your optimal solution for this step. If it's not, then you just discard it and then you repeat the process. You find another set of n samples, you fit the model, find out the parameters, then compute the score using those parameters. So very simple and iterative algorithm. And this can be used very well for the feature matching. So if you can see, feature matchings are something like these. So you have two images. If you look at the left side, if image one is the original image, and then this image is rotated, and you look at this image, but we know, if a human sees, we know that these both are same images but rotate. So the same logic for the algorithms, the computer vision algorithms, to understand, you can use ransack. You identify the key points using sift or anything, and then once you identify your key points, you then use your feature matching algorithm, and then you identify all the features. And then you say, okay, these are all the features which are present in these two images. So if then you can write your own steps also. If so and so degree of feature matching is happening, then we can say these both are same images. Or something like this you can do, like homography, where you have two images but taken slightly at a what do you say, shift in the spatial space. Then you can basically identify all the important features and you can stitch the image together like this. So you can either use for a check condition whether these both are same images, or you can do image stitching using ransack, something like this, where you identify the key important features and then you match those features and you make a image, combined image like this. uh, then so this is a feature matching algorithm. And then after the classical algorithms, which we talked about in the first 3 weeks of this course, we went to the important part, the major focus of this course, which is the deep learning part. And before that, we first talked a little bit about what exactly neural networks are. And then we talked about CNNs and then object detection, segmentation, and so on. So I went a bit fast for the classical algorithms because I'll go a bit slow now on the deep learning algorithms, because the course is most deep learning based computer vision. So I'll go a bit more slow in this deep learning points. So yeah, first thing what we tried to explain or talk about was the multi-layer perceptron. In multi-layer perceptron, which is nothing but you can say it's a normal perceptron extended over multiple hidden layers. So it's called a multi-layer perceptron. In this case, the hidden layer is only one. So the hidden layer is only one. So it's fine. It's just one hidden layer multi-layer perceptron. But usually we have more deeper and deeper, like you'll have sometimes you'll have 30, 40 also. So you can see architectures which have like ResNet 50 has 50 hidden layers, and so and so. So based on this depth which we have, right, like more and more we keep on increasing it. That's why it's going more deeper and deeper, and that's why we got the name deep learning. So it's nothing but it's just artificial neural networks which are more which have more hidden layers. So yeah, coming back. So what does MLP do? We say that if we have a particular attribute set, like attribute zero and different attributes like smell, sound, and shape, this could be your any attributes. It could either be your images, or it could either be your Excel type of a data, or it could be anything. What we try to do is we connect each input node to every other hidden node. So in this case, just ignore this particular part. Uh, okay, yeah. So this is a hidden node. So we connect. If you see, attribute zero is connected to the hidden node on one, and is also connected to the hidden layer node two. And similarly, we connect smell with the same every other hidden node. And now these hidden nodes will be connected to a further another hidden node, which are present in the second layer. So you see this particular is connected to four of these second layer hidden nodes. Similarly, this hidden node is connected to four of the second layer hidden nodes. So in this way, all we're trying to do is we are trying to look at each possible attribute and how it is related to each other attribute. Oh, and so it's not just one layer in what do you say, dependency, but we keep on doing it for multiple layers, so we can see more and more complex relations that can be formed when these particular inputs are combined to hiddens, and these hiddens are combined more to form these hidden layers. So we are trying to see how your particular input combinations and all, what are the relationship between those two, between the inputs with the final prediction y. And then, like you can see, all these multi-layer perceptrons, all the multi-layer perceptrons hidden nodes should have a non-linear activation. Then only it makes sense to have hidden layers. If there are no non-linear activations in the hidden layer, then how many ever hidden layers you increase, it will always be equivalent to just one particular hidden layer. Why? Because it will be if there's no non-linearity, it means there is linearity present. And if there is linearity, we are just adding up terms. We are not really gaining any representation. We're not pushing it in some other what do you say, space or something, or we're not creating more complex structures or anything. All we are doing is just adding and multiplying them and sending it to another node. So such cases are really not helpful. So it's very important and imperative that you have non-linearity present after each hidden node. That only increases the representative power of the multi-layer perceptron. So here in this case, we use a sigmoid nonlinearity, but it's not necessary that you need to use sigmoid. You can always use other activation functions. So these are the commonly used activation functions. So the first one was the sigmoid which we used. You can always use leaky ReLU. ReLU is the most common in nowadays architectures, but people are starting to use more leaky ReLU also. So leaky ReLU and ReLU, they are used in the hidden layers, but after the final layer, if it's a binary classification, you use sigmoid, or if it's a multi-class classification, you use softmax. Softmax is nothing but it's more a softer version of the max function, so you can always look into it. So after the final layer, basically after this particular final output layer, you send it usually through sigmoid activation if it's a binary, or softmax if it's multi-class. Yeah, and all the others you can use in the intermediate layers. So mostly commonly leaky ReLU and ReLU is used. uh, these are other, this is obviously not an exhaustive set. You have more and more activation functions available. And now I told, so what we talked about till now is a forward pass basically. So we have your input attributes X. We then send it to your hidden nodes. We have a non-linearity. They send it to another hidden layer. Again, their non-linearity, and finally you get your prediction. We send it to the output layer. Then they send it to the output activation function, and then based on that you get your final prediction. What this particular class is either class one or class two or so and so. So once you get the final prediction, now we need to know how well is this prediction with the actual value. Remember that for now we are talking only supervised learning setting, and in supervised learning we always have the labels, ground truth labels associated with every input. So this particular input will have some ground truth label. And now once you predict what this particular input should fall into which class, that prediction we compare it with our ground truth label, and we say ki how bad or how good it is, how good my prediction is with the actual ground truth label. So how do we find? We use some loss function, and this is usually a standard loss function figure. So this loss function could be anything. So we can use a MSE loss if it's a regression type of a problem also, or you can use MSE for even classification. But for classification, usually people use cross entropy loss, which is more robust. So cross entropy loss function usually has a structure like this. So this type of a structure we call it as a non-convex structure. Why non-convex? Because you have more than one minimas basically. There is a local minimas and then there is a global minima. In convex, we usually say only there is one minima which is both global and local. So that is a intuitive way to understand. But the formal definition of convexity basically comes that If you draw a line between 2 points in the graph in this figure, all the points in between those 2 points, in between the 2 points which we draw a line at, all the points below that should lie below that line itself. If there are points lying above that line in between those 2 points, then it is a non-convex. So for example, if I pick this blue point over here and I join it with some yellow point over here, there are these bumps which are above that line. So it's a non-convex. Whereas in a standard parabola, right? If you remember, if you see a normal parabola which is like this, over there, if you draw lines between any 2 points, all the intermediate points lie below that line. So parabola is a very good convex graph. So, but usually in deep learning, in MLP type architectures or any deep architectures, the loss functions are not convex. Loss functions are always non-convex, and in fact, this is a more simpler version. Sometimes you'll have more number of higher bumps and like more number of local minimas and global minimas, and that's why it's really hard to identify what the best possible value is for a deep learning figure, for a deep learning architecture, because you sometimes you may never reach your global minima. You might get be somewhere in your local minima, but you feel like, okay, that is good enough for me, and then you deploy it in the real world. But reaching the global minima is not really a guarantee kind of a thing. So obviously there are certain guarantees, but let's not get into the mathematical side of it. So this is a typical loss function which we use for any deep learning architecture. So once you calculate the loss between your predicted y value and your ground truth y value, now what should we do? Now we should basically tell our parameters. Basically, these parameters are nothing but these connections. You can say each connection represents a weight. So and each weight is called parameter. So all these arrow marks which you see, these are nothing but parameters. Those are weights or parameters. So once we calculate the loss, you from a figure like this, or basically you have an equation, you have your loss. Now what you want to do is you want to tell your network, basically you have to tell your weights in what direction do you want to move so that you'll do better and better predictions. So if your loss is a lot, then you move in the opposite direction in a in a bigger step, because your loss was huge, and hence the gradient will be huge. So in that way, basically you keep on telling all these weights, these connections, what direction you have to move, so that you change your values in that way, so that this particular forward pass will give a very good prediction which is closer to your ground truth level. So that is what we do in this gradient descent function. So in gradient descent, we basically make each parameter move in a certain direction following the gradient of the loss function. And why we do that? Basically in the hope that we keep on reaching the lowest point in our loss function. So this loss function, we calculate gradients and we keep on moving such that we reach some minima. Ideally we want global minima, but we want something which is closer to the global minima also, it's fine. So we keep on moving in a direction which is towards the minima. We don't want to go in the upper hill direction, that's why we take the negative of the gradient to move in the downward direction basically. Yeah, so this is gradient descent algorithm. So and what type of gradient descent algorithm are available? We have batch gradient descent, a mini batch gradient descent, and stochastic gradient descent. And the difference between these three is basically in batch gradient descent, we send the input all the samples to at one time. So basically we calculate the loss function for all the samples, and then we calculate the gradient of the total loss function. And then we do one update step. So that is your batch gradient descent. In mini batch, like you expect, you don't take the entire batch, you take a part of the batch, some mini batch of batch size like some 32, 64 or something. You take that mini batch, you calculate the loss, you calculate the gradient, and you make your parameters move based on that mini batch loss which you calculate. So that's why, as you can see here, these steps are more wobbly because you're not looking at the entire batch. So there can be some noise in the gradient which you're estimating. So that's why here you won't go in a straight line towards the minima like you went in the batch. But since you're estimating with half like a small part of the batch, you go in a more zigzag motion towards the minima. And to an extreme case, if you just see one sample and you keep on updating your parameters based on one sample loss, your what do you say? Your variation will be more in your gradient estimation, and that's why your steps will be more wobbly, more up and down, more up and down, and you'll basically reach to a minimum. So this is not a very good way to do for every sample, because then since the variance is a lot, sometimes it'll take a lot of time till you reach your minima. Sometimes you won't even reach your minima. So best way is to use the mini batch gradient descent, where you take part of it and then you can keep on moving. Okay, just to keep it more interactive, why is batch gradient hard to do in real world? We don't use batch gradient in real world. We use mini batch, as you've seen in the examples. Why do you think batch gradient is harder to do in the real world? Maybe you can write it in the chat or unmute and tell me. Any guesses? Why is the batch gradient descent hard to do in real world? We mostly follow mini batch. I explained stochastic is not a good choice because there'll be a lot of variations towards and like in each update step, which is not ideal to reach to the minima. So any guesses why batch gradient is not used in real world? I am audible, right? Maybe if someone can confirm in the chat if I'm audible. Okay. True, correct. As pointed out in the chat, it's memory constraint. So, as you know, in the real world, the examples or like the problems which you solve in real world, the data sets are huge. Like easily they go up to order of 10,000 also, and some other data sets go up to 100,000 also. And again, these are all simple data sets. Like I think it's Coco or something which go into 400,000, or like a lot of data samples are used. Even the chat gpts which you see, right, they're trained on huge data samples, like the entire internet basically. So in batch gradient descent, like I said, you have to update after seeing all the samples and calculating their loss, right? But if you have such huge data, and if you see our GPUs, basically the best GPUs also have maximum GPU RAM capacity of 32 GB. Even if you combine, so how many will you combine? The cost will increase combining multiple GPUs, then providing coolers for them, and basically it'll be really hard. So to avoid all these constraints, people use mini batch, which is a very good estimate for the batch gradient descent. And it's a very good hyperparameter also. The hyperparameter over here is the batch size. So you must have seen in your programming assignments, or if not, it's a very good exercise. You have to like keep on changing your batch size from 32, 64, 128, 250, 128, then 264, and so and so, so and so. You keep on changing, and you can see how the accuracies are changing, and why certain batch size give bad accuracies, why after a certain batch size you won't even get change in the accuracy. You'll get saturated. So you can see a lot of experiments with your batch size. It's a very good experiment. I would highly recommend you people to do that. And once you do your gradient descent, so the for a normal, what do you say, perceptron, one layer perceptron, gradient descent will be sufficient. But since we talk about a hidden layer, right, like multiple hidden layers, simple gradient descent won't be sufficient, because if you keep on doing gradient descent, like you will have to calculate each time what is the loss with respect to this parameters, like these arrow marks, what is the loss with respect to these arrow marks, like, and then again you'll have to calculate what is the gradient of loss with respect to these parameters, and so and so, so and so. It will be a complex task. So instead of that, people came up with a more efficient solution called backpropagation. So to understand backpropagation, you can look at this example. So for a while, you just forget about multi-layer perceptron. Just look at this computational graph. So we call such graphs as computational graphs, where each node has some operations happening, and those nodes are then sent output of those nodes is connected with the other nodes in which in some other operations, mathematical operations are conducted. So this is a computational graph, and as you can see, if you like, the base two nodes describe the variables a and b, and then you have other two nodes which describe what the c and d operations does, and finally another operation e. And now you can see in these yellow colors, we have stored the partial derivatives with respect to each of these variables. Like the output we get C, right? That with respect to the parameter A, what is the partial derivative? Similarly with parameter B. Now, similarly, since D is also connected with B, what is the partial derivative? Now you go one step top. Now output is E. Now what is the gradient of the output with respect to the parameters C? And similarly, we identify the partial derivative of the output with respect E with respect to the parameter d. So storing these partial derivatives actually help a lot, because then what you do is you calculate your gradient over here of the output layer, what with respect to loss function, you calculate the gradient, and then you just multiply with these partial derivatives, and that will be the gradient of this particular output with respect to the parameter c. Now similarly we can take that whatever you get the value over here, we multiply it with this partial derivative, and then we get the gradient of the out loss with respect to the parameter a. So as you can see, we're basically all we're doing is multiplying partial derivatives with the gradient values of the before layer, and then we can easily identify the gradient of that particular parameter in this lower layer with respect to the loss. So this simple multiplication chain rule basically of differentiation actually helps in the computation of gradients in deep learning. So this entire process is called as backpropagation. And as you can see by now, you should all be very familiar with backpropagation, how it is calculated. And this is just for a simple, what do you say, 3-layer network. The same process is you can repeat for all 50-layer, 100-layer networks. So I hope this is clear. Maybe I'll just pause for a quick minute. If you have any questions up till now, you can ask right now, or you can put it in the chat or unmute and ask. So after you then back propagate, and fast after back propagating, basically you keep on repeating the loop, and then you keep on repeating your loop for so and so number of epochs, and then you finally finish your training. So that is the usual standard training process for your multi-layer perceptron or any deep learning architecture in general. Now, sometimes there might be issues where your architecture might not actually, work well. Like for example, there is an issue called overfitting. So maybe can someone explain? It's a very simple concept. We already discussed multiple times. What is overfitting? Maybe someone can put it in the chat or unmute and tell. So we talked about two concepts called overfitting and underfitting. It's even used in machine learning. So what is overfitting? Okay. Maybe I'll. Yes. As posted in the chat, it's correct. When you have low training error and high test error, but not just in terms of errors or training error, test error. Like, what does it intuitively mean? Is basically it is memorization. Overfitting is nothing but you can equivalent it to memorization. And what I mean by that is, if for example I have a certain data set input X, like samples are like 50 or 100 samples. Now I have a very big neural network, like million parameters. Now there are just 50 samples and million parameters. Obviously, what happens is each of the million parameters will memorize what each input sample is. And what I mean by memorization, basically it will memorize, okay, this input sample 1 has class label A. This input sample 2 will have class label B. So instead of learning what is the relation between the input and output, it will just memorize that, okay, if I get an input sample like this, I'll say my class is this. It won't learn the relationship. Why? Because usually the parameters in the neural network are huge. So because of that, happens. The overfitting happens. Sometimes it's not just the huge parameters, but it's something called as the capacity of the model. If you go more in depth into statistical learning and everything, you'll learn these terms. But right now, you can just understand that the parameters are huge, so they're memorizing all the input samples, and instead of learning the relations between the input output. So when overfitting happens, then like pointed out in the chat, you'll see the pattern in your loss functions where the training loss will be very low, but the testing loss or the validation loss, actually, the validation loss will be high. So there'll be a big gap between the two loss functions. So when such a thing happens, when you're training your model, then it means your model is basically very huge compared to the task or the data samples which you have at hand. So things what you can do is either you can reduce your model size or the model's capacity basically, like or what you can do is maybe you can introduce terms like regularization terms. So regularization terms are one such terms. Apart from regularization, you also have batch normalization which can help, or dropout. So we'll talk about these three terms which are commonly used to basically tackle such overfitting scenarios. So in regularization, all we try to do is we basically restrict what the maximum values that each parameter can go beyond. So this is basically the parameter space you can see. So as you can see, if you put a L1 regularization, we make most of the values lie between in this blue region itself. So we don't let it boost up high. So now we are restricting what each weight value can be. So no more memorization can happen. Now it is forced to learn with this restricted space what the relationship should be between input and output. So how can we restrict? Obviously, we can use any type of restriction. If you use L1 regularization, you form a restriction like this rhombus diamond shape, where most of the values tend to go become zero, because you have more this like a, what do you say, a diamond form. You can see like a cone forming in the bottom. If you look from the top, it's not clear, but imagine like a cone forming in the bottom. So most of the values tend to go to zero. And whereas in L2 regularization, you have more of a circle or a spherical type of a shape in the bottom. So values can have still no non-zero values. Parameters can have still non-zero values. It's not like they're forced to go to zero or something. So depending on different norms, basically, you can form different regularization functions. Commonly used is L1 and L2. So you can check how these L1 and L2 actually helps your model from overfitting. Maybe you can do an experiment where you take a very big model, very small data, and then initially will be obviously overfitting. Then you add different types of regularizations, and you can see how the effect is. You can print out the parameter values and see how many parameters are going to zero in L1 and how many are going how many are non-zero in L2. You can do all sorts of experiments to understand how regularization works. And then another technique is batch normalization. In batch normalization, again, concept is basically simple. What we tell over here is, so initially every attribute will have a distribution. Like before this particular step, imagine the inputs are there. Every input attribute will have a particular distribution. Uh, so there's a question in the chat. Can you give another numerical example? Um, so, what do you mean by numerical example of L1 and L2? You mean the mathematical formulation of L1 and L2? Maybe you can unmute and ask, Jitendra. Yes, exactly. For L1, it is mod basically. L1 is basically your modulus function, absolute norm, and L2 is basically your square norm basically. So you have a normal L1 norm and L2 norm in your linear algebra, right? Basically, those itself you apply it on the weights over here on regularization. So is that clear? Is that okay?
Hello, am I audible? Hello.
Yeah, you're audible now.
Actually, in context of this parameter learning, that is not clear to me. L1, L2, I get it. The distance, one is mod, and but how you are saying in this?
Okay, so in this yeah. So in this context, we'll have weights, right? So each weight, we will basically calculate uh, what do you say, the modulus of that weight, and we add it to the loss function finally. Maybe I'll try to write it out. 1 second, just give me a minute.
That loss we are plotting here, that plot function.
No, the
This
plot.
plot is what?
Yeah, this plot are the weights. Basically, this is W1 and this is
Okay.
W2. So what should be the weight values possible? If you use L1 regularization, we are restricting it to fall only in this blue diamond shape, basically.
So it will be kind of a straight line, no? Yes, or what?
Sorry?
Instead of getting that square, hello,
Yeah, the reason of getting
W1
this.
and W2. Yes.
Yeah, the reason of getting the square is basically because if you form the L1 norm, right, you'll have a diamond shape. In when you take the L1 norms values, if you input the values and see, you'll get a diamond shape. And for L2 norm, you'll get a square shape. That's for normal vectors also. So the same concept over here we are applying on these weights W1 and W2. And this red color map is that particular loss function which is being restricted with this L1 and L2 norm. Are you getting what I'm saying?
restriction we put extra what thresholding kind of or what?
No,
The
no.
extra
So
constraint we are putting.
yeah, so how you put constraint is if you have the loss term, like let's just say, just a minute, I'll get the
Take a
pen to.
simple straight line example, and we are applying try to imply suppose any straight line. Suppose some function is there, we try to model with this concept. In
Yeah,
L1 L2 norm we are applying. Can you uh, realize there with this example?
yeah, yeah. Just a minute, I'll just get a pen so that I can write and show it. It would be better. Uh, we'll just try to write it over here only. Just a
Or you take it in work later and also explain me kind of. So other are also there. They don't have that doubt, same doubt.
minute. Yeah, maybe I'll try to. We'll discuss after the class. Maybe I can explain it there, but you can just think of it like this: like you have a loss equation, right? You know the cross entropy loss equation. Yeah, you what you do for regularization is you add a plus some lambda into this weights norm basically. So in that equation, you just add an extra term. You sum the extra term lambda into the mod of w if it's L1 regularization or square of w. And how many w's you'll do? You'll do it for how many w's you have in your network. So you can think of that loss function now will have an extra addition term, and that extra addition term is basically causing this loss function not to be a original figure, but this blue color figure which you see.
Okay, now it's clear. Now you added the lambda. Actually, I was thinking directly to the mod and its square term. So that's why.
No, no, we
Now
had,
it's clear.
yeah, we had the lambda term over there. Yeah. So another after the batch normalize, oh sorry, after regularization, another technique is batch normalization. So what happens in batch normalization is the input, each attribute will assume to have some distribution, and what we do is these distributions actually when you send it to your hidden layer, right? When you do your wx plus b, they actually get shifted. So the statistics of each of these will actually get shifted attribute. Why do we get shifted? Because obviously you're doing certain operations on them, and each attribute can like it's adding and multiplying. So the original distribution gets shifted in different spaces basically. So you'll get yellow, green and blue. What we want to do is we want to again make all of these internal distributions to follow a similar distribution like the yellow one, because this will ensure that your training for the further layers will be simple and follow this particular distribution itself. Otherwise, if once you're getting a distribution yellow, another time you're getting a distribution green, and you're sending it to the other layer, learning will become hard because each of the distribution is different from the other distribution. So the other layers won't know what exactly should the distribution be. To avoid that confusion, we basically try to uh, normalize them, you can say. Basically we're trying to normalize into this one particular yellow curve. And what should be the normalization parameters? This gamma and beta. So gamma and beta basically you try to learn those also with uh, the batches which you get, right? Mini batches, based on those you keep on learning what the gamma and beta is, and you normalize all these different distributions into one distribution yellow, and you send this to the further layers. So because of this, in some way we are trying to avoid the covariate shift. Basically the shift is called the internal covariate shift. We are trying to make the training faster, and in certain ways it also makes the relationship learning better. So how exactly it is done, that is a bit technical and mathematical, but you can always look into the original paper of batch normalization. When they propose it, they talk also exactly how it is helping to overcome the overfitting also. uh, Apart from that, it is also speeds up the process because now we are scaling and normalizing all of them into a similar distribution. So in this way, batch normalization is done. And after that, another technique which was very popular, which is still people nowadays use it, is dropout. So what we do is, if you look at the normal traditional MLP, you have your input layer, all the layers are connected to every other hidden layer, so and so with the final layer. But in dropout, what we say ki, why not just drop few connections in between the input and the hidden layer, and similarly between hidden layer and the output layer? We just keep on dropping some connections. Now, what we are trying to do is we are forcing the network to learn the relationship. So why I say that? So if you take the original problem only, when I talked about overfitting, we had a lot of parameters, less data. And what I said, each of these parameters, which is each of this arrow mark, will try to memorize what that input will be, what that label for that particular input will be. Rather than learning the relation, it will just memorize. But now, if I'm breaking off these connections, right, suddenly in between, randomly I'll break the connections in between. So now, since I'm breaking the random connections, the other parameters which previously was memorizing are now forced to basically learn the relationships. It can't memorize anymore because the loss will increase. Because I'm dropping these connections, the loss will increase. So because the loss will increase, we then make sure that the parameters are pushed in the direction which is learning the relationship rather than memorization. So intuitively, dropout is doing this basically. You randomly drop connections, which is forcing the network to learn the relation rather than memorization. So I think this is clear. Maybe I'll just pause till here. If you have any questions, you can ask. Dropout is always in training phase. Okay, very good question. So always remember, dropout should be only in training phase. So when you're doing testing, you can't do dropout because your test value should always remain the same. Like for example, what I mean by that is, once you do your training, everything, whatever regularization, whatever you do, you fix your training. You say, okay, this is my final training model. These are the final parameter values, and then you take those parameter values, you freeze them, and you do your testing. And how many ever times you test, you should always get the same accuracy. You shouldn't get different accuracies each time. But if you use dropout, if you look at the architecture of what the dropout should do, it is dropping connections. So if in test phase you use this dropping connections, your accuracy won't be same. Your accuracy also will keep on either sometimes more, sometimes less. But we don't want that. So always remember, dropout should be used only in training phase. So that is highly important. Never use dropout in testing phase. So that's why if you remember, in PyTorch, we call something as model.eval, model.train. So I always said in coding also, before you do testing, you always should call model.eval, which basically tells PyTorch that all the operations like dropout or whichever operations will cause the random fluctuations in the accuracies, those all should be frozen, and only static, what do you say, stationary parameters should be present. It means that your test accuracy should be the same how many ever times you run it. So that's why model.eval is very important in PyTorch also. That is what basically differentiates between using dropout and train and test. Okay. And after the MLP, next week, after the MLP week, we talked about convolution. We moved on to convolution, basically convolution neural networks. And major operation in convolution neural networks are convolution operation. So this is what it does is, basically imagine you have a filter, this blue color filter. So we have this filter, we place it on the patch. As you can see, we are placing it on each patch, we are moving it, and whatever patch we place, we calculate element wise multiplication and sum of all those element wise multiplication, and you get the output, which you can see on the right side. So simple convolution operation. What the parameters now in this case, like in previous case I said the arrow marks are the parameters, but now in this case, whatever values are there in the filters, those are the parameters or weight matrix. So now the goal of the neural networks are to learn what should be the weight values, such that after convolution, the outputs I get should make sure that I'm learning good relationships, and it will help me in classification. So that is what the goal of neural network becomes. And then we talked about another type of operations called pooling operations. And in pooling operations, the major thing is we want to downsample. Basically, we want to reduce the input size, height, and width of this particular image. Now this could be either the input image, or it could either be intermediate image, also intermediate layer output basically. So whatever it is, we want to reduce the height and width of this input. So what we do is basically, to downsample operations, we use the pooling layer. If you want to reduce it by half, usually we use pooling with a stride 2. If you want to reduce by 4 times, I think it is stride 4. So you can just change the stride values and you can see how the pooling affects. So two different major pooling operations what we use is for max pooling and average pooling. In max pooling, what you do is you have that filter of that. Sorry, you take that patch. If you say 2 by 2, you see a 2 by 2 patch. If a 4 by 4, 4 by 4 patch, and out of that patch in that input image, whichever is the maximum value, you only output that as you only output that particular value, and you get a smaller image output basically compared to the input. Whereas an average, whatever patch you are looking at, you take the average of all those pixel values or elements and you output them. So average is basically kind of looking at all the values, and max pool is kind of just picking one max value and looking at it. So you can see these are some of the comments. You can comments as like advantages. You can see max pooling basically preserves more detected features, and it's most commonly used actually. Whereas average pooling, it downsamples the feature map. At the same time, it's kind of averaging out the features which we're learning. It's also used, but most commonly used is max pooling. I think average pooling was used more in LeanIt. It was proposed in LeanIt, which is in 2013. But yeah, you can always experiment, like I said, with max pool and average pooling, or how the accuracy values change and affect. And then we talked about fully connected layers in convolution neural networks. So previously we talked about MLPs, that is where you have just your fully connected networks. We don't have any convolution. But usually in convolution neural networks, we also have at the end a fully connected network. So how do we get that? Basically, we let's assume this is after the final convolution layer. We get this particular output, the small what do you say, matrix. Now this particular matrix, we first flatten it out. So you can use any type of flattening operators. You can either just unroll it, like you make this matrix, you unroll each element and make it into a vector, or you can, if you have multiple channels, sometimes you can do global unrolling also, global average unrolling, and there are multiple operators. So what we are trying to basically do is, in this case, it's a simple matrix you have, you unroll into a vector, and now this you can treat it as your input in your MLP, and then you keep on connecting to your hidden layers. Each element is connected with each other node in the hidden layer, and so you do your standard MLP network. So only major step is this particular unrolling. How do you unroll is also a good thing to see. You can either do a simple unrolling of each element into a vector, or if you have multiple such matrices like channels, basically, you can either do unrolling of all those elements and make a very big vector, or you calculate the average of all those channels and then unroll it into a vector. Many operations are possible, but all you have to do is unrolling. What type of unrolling you do is not it depends, and it changes your accuracy. So a typical neural network consists convolution neural networks consists of these. So as you can see, you have your input image. The first convolution, after the first convolution, the outputs look like these. So as you can see, features being learned, what exactly the intermediate convolution layers are learning actually. As you can see, in certain shapes are being learned, certain intensities are being learned, and certain complex. As you go further, deeper and deeper, those become more and more complex. Like here, you learned mostly intensities or the bigger shapes, like the car hood or the bottom part of the car. If you go further more, you features become more and more detailed, like certain head what do you say, the headlights are being learned, or the side mirrors are being learned, or certain angles are being certain shapes of the car are being learned. Obviously, if you go further a point, you can't really understand what it is learning, because for humans, we can't really observe and say what exactly is it learning beyond a certain number of layers. But intuition is that, as we can see, at least for the first few layers, that it's learning complex features which are present in the object, and basically more and more deeper you go, it combines those features and creates more and more complex objects that is being learned. And finally, after your fully convolution operations, you have a fully connected layer which will basically connect to your classes and will say ki, okay, which class this particular input sample belongs to. And then since it's a car, the most probability will be for the car compared to the other classes. So this is a typical convolution neural network. I hope this was clear. I'll just pause for a quick minute. If you have any questions, you can ask me. And then after that, we talked about explainability. So like one part of explainability was actually visualization of the intermediate layers, which I just told. So that is actually one part of explainability which people used previously. Like I said, it's really complex to understand beyond a certain number of layers. People came up with different techniques. Popular technique is CAMs or class activation maps. And what this says is, so the last convolution layer, what you can do is you can take that convolution layer, do a global average pooling, identify and make a vector basically. And now each of the node in this vector is connected to the particular class. And like for example, if I focus on this class called Australian Terrier, so you will have weights, right, for each of these connections. Like I said, each of these arrow mark will become a weight. So now these global average pooling, as you can see, each color is corresponding to that particular node. How much is this particular channel is contributing to this particular class is what we're trying to learn. So this W1, W2, Wn, what it learns is what should be the weights of these channels after the last convolution, which contributes to it belonging to this particular class called Australian Terrier. Now, similarly, the weights will be different for other classes. You can always see what it is looking at, but intuition is what is happening in the below. So each class activation map, each class activation, which is basically these colors, green, red, and blue, those will have its weights associated, which is W1, W2, Wn. And then adding all of them together, you can see exactly what this particular where this particular dog is present in this particular image. That is what this class activation map is doing. So you take a trained neural network first, and then you add the global average pooling, and then you do another retraining to learn these weights, which will basically learn the priorities of these maps. And then once you finish those trainings, you can then add them up with the weight values, and you can see if you want to look at the Australian class in this image, where is this? It is looking where the neural network is looking. It's looking at this position, which is actually the dog where it is present. So this was a very popular method, and then people came up with variations of this called GradCam. Then people came up with GradCam plus plus also. So there are other variations which are possible, but this was actually one of the pioneering works for explainability or understanding of the CNNs. So these are some certain other examples using CAMS itself. So where the neural network is looking at when it is saying it is belonging to a particular class, and in this case, the class is the Briard, which is a type of dog. So you can see in this particular image, it's just looking at the face and easily classifying. Whereas in this particular image, it's looking at these eyes also and a bit of part of the nose and everything. And again, if the full body, so what you can understand from here is if the full body of the doggy or dog is present, it if just the face of it is enough to identify. But if a zoomed in version is present, it's not really clear because then you can't really associate all the other features, right? Like you can see here, it's along with face, certain parts of legs and tail it is associating to conclude it as a dog. Whereas if it's only face, it's not really clear. So that's why the probability is less, the confidence is less compared to the other confidence. So these are just some interpretations you should learn. Uh, how you should interpret your outputs also, you should basically learn. So this will come with experience only when you keep on training a lot of networks and understand what the neural network is trying to do. You can make your own observations and understanding. Similarly for barbell also, you can see a similar type of examples where it's mostly looking at these two circles which are present or connected with some element within it, and based on that it is being basically detecting it as a barbell or not. So, like I explained, CAMS obviously is not the best method available out there because of these particular cons. Sometimes it becomes really complex to again retrain the model, and especially if the task is complex like object detection or segmentation, it's really hard to again understand what it is trying to interpret and do. And retraining also, like interpretability and accuracy, basically it keeps on going hand in hand now, because since I'm retraining it again, when I'm retraining there is a chance that my original accuracy will drop, because now certain weights are being accommodated, or the features are being accommodated to interpret the model. So because of two contradicting loss functions, your overall accuracy might come down a little bit. So, and another, like I explained, retraining is hard to do when you already have a trained model. Again, you have to retrain. So, again, pros are again that doesn't require back propagation. You don't have to back propagate everywhere, just those weights. And then self supervision. You don't really have to learn any, create any variables, ground truth labels, or anything. You just give your input image, and the trained model on itself, it'll learn the class activation maps. Okay, a quick pause if you have any questions if up till now. Now you can maybe ask right now. Then after this, we'll talk about the object detection and segmentation models. Okay. So moving on, after explainability of the models, we then talked about object detection. Object detection task, like the task is simple. What we want to do is, in a given input image, we want, like for example, if you take this dog image itself, we don't want to just classify it as dog. We also want to say where the dog is present in the image. So we basically want to draw a bounding box across this dog object, basically. So now the task is a bit complicated. Instead of just saying which class with which confidence, you have to predict the class, but at the same time you have to predict the bounding box coordinates along which this on which this particular class or object is present. So here, obviously, you'll have two tasks combined: classification to say which class, and regression to identify the coordinates of the bounding box. And over the past decade or so, I think even before that, people have mostly used two-stage object detectors, actually, called the faster RCNN family, or the RCNN family, and they have come up with multiple variations. But basic logic is this: you have your CNN backbone, which is usually your feature extractor. Nowadays, people are replacing these CNNs with transformer based also, but any whatever it is, you use a backbone network to learn the features, and that will be sent into a head network which has two parts. One is the region proposal, that is identifying the regions in the image where potential object can be present, and then once you identify those regions, you narrow it down by localization and classification module. So in that entire region, you now narrow it down to what exact location is, and then you also classify whether what type of a object that particular thing is. So here, since it's two stages, one stage is identifying regions, and then second stage is narrowing down the regions. So that's why it's a two-stage detector. Whereas in one-stage detector, we overcome this region proposal step. We just use a head network which directly from the features extractor identifies the bounding boxes. It directly narrows down. It doesn't identify regions of interest and then narrow. So these are the two difference between the one stage and two stage detectors. One stage detectors are relatively new, I would say, compared to the two stage. One stage started coming from 2014, I think, when the first YOLO and SSD models were released. Whereas two stage was previously also there. It was there since 2010, I guess. I'm not sure about the dates. You can always look in. The best two-stage detector, at least uh, uh, till few years back, was the faster RCNN. So, like I said, there are two stages. The first is your there are two stages: your region proposal network and your your classification and localization network. And this particular part is your backbone, which is your feature extractor. So, like I said, what it does is you identify your features, and this after nine, whatever you have the output after the number nine, that will go into first the region proposal network, and those region proposal networks identify the objects of interest where the particular regions are interesting. It will crop those images out, crop those regions out, and send that input to the classification head along with the feature extractor, and then you identify basically from those region proposals, and you narrow it down to what should be the location of the object. So I, again, maybe I'll repeat once again. So here we have the RPN network where you take the input from the feature extractor, and then you identify what the regions are interesting. You crop those regions out. You send those cropped regions along with the features which you learned from the backbone into the classification head, and then you use ROI pooling, which is basically used so that all of them can like sometimes the dimensions might be different of the cropping regions, right? So because of that, we use the ROI pooling, and then after the pooling layer, we then send it to the normal fully connected layer to identify what class and what bonding box coordinates are. So this is your faster RCNN network. Similarly, this is your typical YOLO architecture. So I've used YOLO V4 over here, but nowadays YOLO V8 also came. So, but most of the YOLO V8 and YOLO V7, those all basically have a similar template. So from what YOLO V4 has been used. So that's why I used YOLO V4. But in real world, actually, the pioneering architecture is YOLO V8, which I think was released in this year only. Yeah, it was released this year. So what YOLO architecture does is you have a similar backbone architecture, and now we don't have any region proposal network. All we do is we have a neck network. What it does is it takes the inputs from each of the backbone network and it tries to first downsample it to learn the features better. These additions are basically to preserve the semantic information. So what the semantic information does is basically, if in the input image, if my object is present over here and the object of a present, like object 1 is present here and object 2 is present here, so there is some spatial relation between object 1 and object 2. So when you send into the first backbone, you keep on reducing the original input image into smaller and smaller and smaller size. Now from here, if you upsample, remember when you're upsampling, you're going from smaller dimensions to higher dimensions, so there are a lot of gaps to fill when you're upsampling. And when you're filling the gaps, it might be possible that object 1 and object 2 won't have the same spatial relation as the original image. It might be like they might be closer or differently oriented. So to maintain the relation, spatial relation, we add those corresponding layers. So when you add these corresponding layers, when you're upsampling from the corresponding downsample layers, we say ki we are preserving the spatial relations between the objects or the elements present in the original input. So we do that particular type of an operations. I mean, we actually there are a lot many operations which happen in YOLO V4. Due to time constraints, you can always look into the paper or you can ask me after the class, I can explain. But there are certain more operations happening. You predict after the neck network what in three different scales. You say ki all the smaller objects can be detected, bigger objects are detected, medium size objects are detected, and even the smaller objects are detected. So in three different scales you predict basically from the YOLO V4 architecture. So advantage of using YOLO V4 is the multi-scale. Actually, in faster RCNN, such multi-scale step was not there. In YOLO V4 and YOLO V3 actually started multi-scale, where you predict even the smaller and smaller objects, because now you are forcing the network to output at three different scales. So that's why this is again famously used in real world scenarios. And then after object detection, we talked about segmentation, and major operations in segmentations is the upsampling stage, which is also called the transpose convolution. It's another term is deconvolution, which people don't use in deep learning, as I've explained previously also. When you use the term deconvolution, actually there's nothing term called as deconvolution in CNNs. It's used in digital processing. It's a different operation in itself. So if you're talking in context of deep learning, we always use the term called transpose convolution, which inherently is what upsampling is done. So if you have your input like this, and if you want to do a transpose convolution with a kernel like this, so you follow these particular operators and your output will now be a bigger size than your input. So previously your input was your 2 cross 2, now your output is 3 cross 3. So let's see step by step what is happening. So what you do is you first take the zeros and you replicate, you duplicate those zeros in a kernel size space. So if the kernel size is 2 cross 2, you enter all 0 0 0 in 2 cross 2 space, and now you add them with the kernel 4 1 2 3, and similarly you add them, sorry you my bad, you basically multiply the 0 with 4 4 4 4 1 2 3, and you get 0 0 0. Similarly, you multiply 1 with 4123, you get 4123. Similarly, you take 2, you multiply with 4123, and since the position of 2 is here, you have your corresponding elements here 8246. Similarly, with 3, the position is at the right, bottom right. Similarly, you'll see 3 multiplied with the kernel 3, 4, 3, 1, 3, 2, 3, 3. You'll be adding it at this terms. And then you add all these values, and that will be a final output. So I think the operation is clear, but maybe I'll just pause for a quick second. If anyone has any doubt in this transpose convolution operation, you can ask. Okay. So I'm assuming it's clear. So in this way, transpose convolution works, which is actually a very important step for your segmentation part when you're using your decoder. So you use transpose convolutions to go from the smaller spatial dimension to a higher spatial dimension, upsampling basically. And now after that, there was another important convolution operation called dilated convolution. So what the dilated convolution says is, so the uh, uh, the top part is the output, the bottom part is the input. There is also a kernel in between, which is not present. Like let's assume the kernel also is present in between. If you have a normal convolution, if let's say the kernel is 3 cross 3, so the kernel basically the output, which you can see this particular blue part, you is basically seeing all these 9 elements from the previous layer, because here we have that kernel, we fit that 3 by 3 kernel on this patch, we do that convolution operation, which is element wise multiplication and addition, and the output is this particular value. So inherently what you can say is this output value is looking at only 9 elements. But if the dilation is 2, then what we say ki we want to make sure that this object is looking at all these elements, which is I guess uh, um, 3 and 4. This is almost I guess 12 elements. So it is looking at 12 elements rather than just looking at 9 elements. Now if I similarly want to increase my dilation to 3, it will look at even more elements. So bigger spatial region it is looking at. So as you increase your dilation, it will keep on increasing the region at what it is looking. The spatial region is what it is looking. So why do we use dilation then? Why can't we just use a bigger kernel matrix? Can someone answer this question? Why can't we just use a bigger kernel matrix like a 4 cross 4 kernel matrix instead of using a dilation too? What will be the difference? Because if you use a 4 cross 4 filter also, you'll still see these 16 elements. If you use a 3 cross 3, you'll see 9. If you use 4 cross 4, you use a you'll see 16 elements over here. Sorry, 5 cross 5, you'll see 25 elements over here. So why can't we just use a 5 cross 5 filter here? Why use a 3 cross 3 with dilation 2? Any guesses? You can put it in the chat or unmute and answer.
I think that will introduce some sparsity in the.
No, no, it's not related to the sparsity. No.
Okay.
So it's actually basically think of it in terms of computation. So if you have a 5 cross 5 kernel, and if you do a convolution with a 5 cross 5 kernel, you'll multiply, you'll have 25 multiplications, and then you'll have to do 24 additions. But if you use a 3 cross 3, your additions are still less. Additions and multiplications are still 9. But you're skipping the values and looking, you're adding and multiplying these bigger values of a different size. So what I mean by that is you look at the blue spots over here. So the blue spots are what are multiplying with the kernels, and adding the multiplication values of these blue spots with the kernel is this output. So with dilation, you're skipping some values in between which are not taking part in the convolution. So the operations done over here in dilation are still as you do it for a 3 cross 3, but you still look at a bigger picture, which 5 cross 5 would look at. So that is why you use dilation operations. So you want to look what a bigger filter would look like, but you want to also remain in the same operations. You don't want to increase the number of operations. So that is the advantage of dilated convolutions. I hope that is clear. Okay. And then after dilated convolutions, what we talked about is metric learning. So metric learning is again an interesting topic. We also see metric learning in future topics also, like self-supervised learning and all. But here the basic metric learning concept is nothing but similarity learning, you can say. So what we are trying to learn is, if given two input images like x1 and x2, are these two images similar or not? Basic objective of metric learning is these. You want to learn a neural network which will take two inputs x1 x2 and say whether these two are similar images, or whether these two are dissimilar images. And based, how do we do that? We have a backbone network which is a convolution network. So it could be a resonate 50 or anything. And then you send the x1 input to this backbone network, get an encoding which is your fx1. Similarly, you send your x2 to your backbone network. Make sure that this backbone networks are same. Like, you're sharing the network over here. You're not creating two separate networks, but you have to share the networks, convolution network. So you send the x2 to this convolution network, shared convolution network, and you get the embedding fx2. Now, in a simple way you can understand is, instead of using big loss functions and all, you can just take a cosine similarity also, or you can just take cosine similarity between these two fx1 and fx2. Why? Because these are vectors at the end of the day, in some higher dimensions, but at the end of the day they're still vectors. You can use a simple cosine similarity instead of this block. But what happens is, cosine similarity, like we all know, it's not very accurate when you want to actually learn big operations, learn big relations in that images. So because of that, we are trying to come up with more and more what do you say we try to come up with more and more unique similarity functions, like your cross and contrastive loss, triplet loss, or any other type of a loss. So in this case, if the loss similarity is like, you can see, if x1 and x2 are same, then the similarity between them is small. Whereas if x1 and x2 are different, you'll get a higher loss. So, and based on these way, you learn the model whether it is able to say whether it is a same image or different images. So how do training happens? Maybe I'll explain it a bit clear. In training, what we do is, we take each input x and we take another image from that particular class, and you send it and you train. And since it's a ground truth over here, should that be that since these both are the same, the output should say okay, the class should be the same class, or the score should be basically zero or close to zero, since they are the same class. And then we also take x1 and the corresponding x2 which is not of the same class, and then we do the training again, but now this time we want it to predict as output as 1 because they're of the different classes. So in this way we do the training of metric learning. And what loss function we can use? uh, okay, so here we have several loss functions, not just triplet contrastive. There are a lot more loss functions I've explained in that particular week. But if you want to know, maybe I can show that slide from that week 8 again. Sorry, week 7, I guess, week 7 again, to discuss what type of loss functions were used. But yeah, typically we use a contrastive loss, which is very common and very popular nowadays. But any loss functions can be used. Even cosine similarity can use, but if it's working, you can always use cosine similarity also.
I have one doubt. Like earlier, we discussed about this transpose convolution
Yeah.
and then dialectic convolution. So, what context that is relatable?
So in transposed and convolution and dilated convolutions can be used in any scenario or any convolution neural network to increase the field of view what you want to see. Transposed is mostly used in segmentation networks where you have an encoder and decoder, right? In decoder, we use transpose convolution because we are going from smaller size to higher size, bigger size. That is what decoder does, right? Decoder goes from smaller spatial dimension to higher spatial dimension. So how to go? We use transpose convolutions in decoder, and that encoder decoder is mostly used in segmentation architectures.
Okay. But then we have option to use this as convolution rather than using the default convolution.
No. In segmentation, you will use default convolution in encoders because, see, segmentation has two parts, right? Encoding part and decoding part. In encoder, you'll use your regular convolutions. In decoder, you'll use transpose convolutions. You can't replace transpose with regular convolutions.
Okay, okay, got it.
Uh, can you mute yourself if there are no further questions? Thank you. So after metric learning, then we talked about recurrent neural networks. So in recurrent neural networks, we there are different types of recurrent neural networks based upon the task which we have. There are this is a simple one to one. There's not much recurrence happening, but mostly recurrence starts from this one to many. So if you have your only input is one, but you want the output to have multiple steps, then we use a one to many type of an architecture. Similarly, in many to one, this could be like a video classification. If you have different frames of an image and you want to classify that entire video, what it is, you take different input frames and then you classify. This could be many to many, could be like language translation. You have a sequence of words in one particular language and you want to translate it to another language. This type of many to many could be video frame classification, where in each frame of the video you want to classify what the particular classification is, like what action or what classification is happening in each frame. So this is another many to many architecture. And the first one you can take as an image captioning task, where your input is one image, your output is a sequence of words, like what that particular image is described as. So depending on the task, you'll have different types of RNNs. And in RNNs, basically we talked about is these three major what do you say operations, or these three major blocks. One is your standard RNN block, one is your LSTM block, and one is your GRU block. So LSTM stands for long short term memory block. GRU stands for gated recurrent unit. So we'll talk about LSTM first. So logic behind LSTM is that in simple RNNs, you couldn't look at a longer sequences in your entire input sequence. Like if you had the input sequence to have longer steps, the typical RNN could not retain information from this time step to a previous time step, which is a lot of steps behind. So this retention power will decrease if you use a typical RNN. So to increase the retention power, people came up with LSTMs, and they came up with three different gates. Forget, it's called forget gate, update gate, and I guess another was read gate. I'm not sure. Maybe you can just look into the term. So they came up with three different gates, and what each gate was trying to do is, yeah, output gate. Sorry, it was forget gate, input gate, and output gate. And forget gate basically tries to learn the information which it has to forget from the previous context which it is getting. So instead of sending all the previous context information into this particular cell, you know okay, some information is not needed, so it's okay to forget some information. Similarly, other two heads also, other two gates also work in a similar way. Output gates take the input, the context vector, and say what all should I send to my next particular cell. That will be my output gate. And update gate, what it does is basically you know the input, you know the previous information, and now you update your own information. In this particular time step, you update your own information, and that is what your update gate does. People just combined the two gates of from three gates of LSTMs and combined two gates and went to a GRU. It's just an extension which is more efficient because we have lesser number of gates. And operations are again very similar. Basically, what we want to try to is retain important information from previous time step, update the information what you're getting with the current input and the previous time step, and then you retain certain information and send other information as an output to your next cell. That is what these operations in RNNs usually do. And major important thing was the back propagation to time. So previously, when I talked about back propagation, it was only uh, in one particular input. Like there was no dependency on different hidden layers, like a what do you say? No dependency on different time steps. But in back propagation through time, there was a dependency on different time steps. Like for example, this particular sequence, right, S0 to S1, S2, S3, these are all sequences which depend on each other, and the weight matrix which is part of these sequences, because we have a shared matrix, right, shared weight matrix. Now this obviously shared weight matrix will be part of computation for each of these S1, S2, S3, and S4, which finally calculates loss. So now if you want to calculate the gradient of this loss with respect to W, you know कि we have to calculate all of these intermediate dependency of W with all these S1, S2, and S3. That is what this particular statements are saying. We know that L4 depends on S4, but S4 also depends on S3 and W. It's not just simple W like we had in previous MLPs. So now what we try to do is we basically try to calculate two different parts, explicit and implicit, where in explicit uh, we calculate a ds4 with respect to w, treating s3 as constant, whereas in implicit we sum all the other gradients which we get from s3, s2 and s1. So that is what we do. So if you look, S4 is nothing but sigmoid of W into S3 plus B. In explicit, we just calculate the partial derivative of S4 with respect to S3, like we normally do. We keep S3 constant. In implicit, we calculate what S3 will actually have the partial derivative, and inherently S3 will have dependency on S2, and then we calculate what S2 will have partial dependence on with respect to S1 and all. So if you look, this will be the expansion. I'm going a bit fast in with respect to time. You can always watch the lecture videos when of this particular week. I've explained this in depth. I think it was week 9. You can always watch the recorded lecture of week 9 of the live session. I've explained in depth of each step how we are going. But in interest of time, I'm going a bit fast with the mathematical derivation. So as you can see, this will be the derivation ds4 with respect to dw. We divide it into two parts: s4 explicit, where we keep other terms constant, and implicit, where we differentiate ds4 with respect to ds3. And now we calculate what ds3 with respect to dw is. So it's like what is it? Since it has its own recurrence, you expand it further. And now since s2 has its own dependence, you expand s2 further. And finally, you come till s1 and you stop. So in short, this entire ds4 by dw is this entire big equation. And to sum it up in terms, basically you identify all the similar terms and you can get summation of k is equals to 1 ds4 by dsk into the explicit term, which is your dsk by dw. So finally, if you want to calculate your loss with respect to a particular weight, you do this basically: loss with respect to that particular first sequence st, and then you calculate all the dependencies that st had on its previous time steps, whatever from k is equal to 1 to t. These are all the explicit and implicit. So in this way, we calculate the back propagation and we send it back in time. So this is the overall back propagation with respect to time. So maybe I'll just quickly pause. I know I went a bit fast. If you have any questions, we can ask right now. Or I would suggest maybe you can look into the recorded lecture also. That will be better.
Is there any way to see, like in our practice, how this derivation work on some input, some sentences or some images like that, or any sequential input if it is available?
Uh, that might be, you're basically saying ki at each step you have to print the values and see what is the values.
Yeah, yeah.
You can try, you can create your own RNNs and try. Maybe you can keep your weights to be small. It'll still be, because there'll be a lot of values. You can still try to maybe do it. You can create a small RNN PyTorch network, right? And in that you can visualize the weight values and you can see. But it will be a bit hard still, I would say, even though if you keep it small, because this particular dependency will depend on a lot of input sequences and they keep on adding up. So you'll have to write a neat code where each output, when you're getting, you're labeling it properly, and you then print out something like this equation which you're having down, if you want to see how back propagation is happening. You can obviously print out and see, because these operations happen in PyTorch. You can definitely print and see the values also, but you'll need a little bit more understanding of how the RNN is coded in PyTorch and how the outputs are coming in PyTorch and those things.
Okay.
Yeah.
Thing is like, so is it just like the gradient descent?
Yes.
We calculate the loss. So similarly here we calculate with respect to a sequence.
Exactly.
And then
Exactly. It's a gradient descent only at the end of the day. But to this is a gradient, right? How to calculate the gradient is what we're trying to figure out. But once you get the gradient, you do your gradient descent.
okay. Then we will get for every step. So that's where we this time step is added.
Yes. Previously we had only one loss, but now since we have output, we have multiple steps, right? So multiple losses will be there.
Okay, and this step is calculated based on the token. For example, if it is sentence, then one character, or if it's video, like one frame. So how this
So
thing is calculated here?
so if you look at this example, So for example, in this case, if you have an example like many to many, so your input will be 3 units, 3 time steps. You take all the 3 time steps input, you send it into your RNN, and now you'll have 3 losses: L1, L2, and L3. This will be your losses. So it depends on what task you have also. If your input is multiple time steps, you take all those, you send it into your RNN, and then outputs will be only 3. Number of outputs will define number of losses you want. Remember, output time steps will define how many losses you want. In this case, the output is only 1, so loss will still be 1. But in this time step, the outputs are 3, so there'll be 3 losses.
Okay. And this batching and all other CNN concepts are applicable here, like number of time steps I can complete in one batch. Like that. I'm just trying to compare this with CNNs.
Yeah. So batch size and everything you can use over here. You can add your regularization terms. Even you can add dropout terms also. That should also work. Batch normalization works. All the basic elements which are not certain to CNNs, right? Like convolution operation. Like you can use it over here. All the other extra modules.
So how this batching operation will work here?
What
Because
do you mean by batching?
batching means just like in CNN we have concept of batch, right? We can specify the number of batches in
So
CNN.
batches is an input, right? So batches is input, right? So
Batches.
so the so that's what I'm saying. Batches is based on input. So that is irrespective of whatever network you take. You if for example if you have 1,000 images, you part those 1,000 images into like 32, 32, 32. So and so you'll divide, right? Each batch will have 32 and you'll have some m number of batches. Now instead of images, you can take like for example words or sentences. Each sentence you can treat it as one image. So you'll have 100 sentences, and instead of sending those 100 sentences at a time, you can divide it into batches of 32. You send 32 sentences as a time.
And that depends on the total number of time steps or total number of inputs.
No, that has no time steps. So batches. So I think you're confusing between how to create your batches. So
Yeah.
batches has no time step relation over here. Time step is basically if you have like okay, if your RNN input should be an image. So here the time step is 1 because your input itself is one word or one image basically. But if you want your input to have input dependencies to have multiple, like if you have a sentence, there'll be 10 words, right? So input will take 10 words at a time. So that's why the time steps will be 10. But those all 10 words together is still just one image, right? One particular sample, right? So doesn't matter what your time steps are. Your sample will depends on the number of batches you create. In that sample, you can have 10 time steps or 3 time steps, or when I mean time steps, I mean words. If you want to go character level, you can say how many characters you want. So each of that particular sample can have n number of time steps. That doesn't matter. But how many samples you have, you divide those number of samples into certain batches, not each time step in the sample. You don't divide that.
Okay, so basically time step is the basic unit irrespective of number of sentence or number of words in the sentence. For example.
Uh, okay, number of so that's what I'm saying. So you can treat the word like, for example, if I have a sentence like this is a English course. So this is an English course. I think it'll have like 6 words, right? And those, if I want to send as an input, I'll have 6 time steps, basically 6 input steps, basically time steps, because I have sending 6 at a time, kind of a thing. And there'll be some tokens in the starting, like end of the sentence and start of the sentence. You can ignore that for now, but that entire sentence is itself one sample. Like that, I'll have multiple samples in my data set, like multiple sentences in my data set. Each sentence, that entire 6 words, is one particular sample, and that will be sent as an input. And that word, you can call it a time step over here if you want. But batches and all that you divide based on your entire data set, which is
Okay.
all the sentences together.
Okay, got it.
Okay. So after that, then we talked about transformers, and specific, we talked about the major operations in transformers, which is your self attention and then multi-head attention. So I'll again explain this in a bit fast pace since we have limited time. So here you can what we try to do is we basically have some input, like for example, if you can see input is thinking machines. We first create a word embeddings of those. The word embeddings, like I always say, it's a standard NLP word embeddings you can use, like word to vec or ngram models. What word embeddings does is we basically take those words and we create vectors of those words. Like thinking is a vector representation of x1 and so on and so. So we take these x1s, x's basically, and we multiply with our weight matrices. So we have three important terms called query, key, and value. And how to get these three important terms? We basically multiply each of the input with corresponding weight matrix. So x into wq is your query matrix, x into wk is your key matrix, x into wv is your v matrix. And then once you get your query key and v value, you do this operation with softmax of query into key transpose, which is basically you're doing your uh, self attention major thing over here. You're looking each value, each input word, how it is depending on other input words. That is what this particular thing, because if you think about it, this is nothing but a dot product in itself. So we are basically finding out the dependency of each input word with itself. That is why we are saying this is a self attention. You're finding the attention of each input word among all the other input words itself. So after we do this operation, and then we multiply with the value v, we get a vector called z. So now we do, this is a simple self attention. Now if you actually use it in the transformer, we use 8 such heads. So this is one head operation. We use 8 such head operations. So this is how it looks actually. So you have 8 such WQ matrices, 8 such WK matrices, and 8 such WV matrices. You'll have your input, uh, which is your X. Then you multiply this with the first head WQKV, second head WQKV, and so and so up to the eighth head QKV. And then you get your corresponding QKV values after each head. Basically, you'll have 8 QKV values. And all of these 8 QKV values you send into this operation and you get your corresponding 8 Z values. And now all of these 8 Z values, you multiply it with a big W matrix, and you finally what output you get? This is your Z matrix. Now this Z matrix, you send it as a input to, you send it this to the next encoder layer. Basically now this one together is the encoder layer. That is what you see over here. So you have your multiple head attention, which is these operations, and you get your Z output. And then there are a few other steps which we do layer normalization over here, and then we send it into the feed forward. So feed forward is basically so that we maintain the dimensions such that the dimensions don't blow up. So that's why we maintain the dimensions, and that's why we do the feed forward to make sure that the z is not blowing up into bigger and bigger dimensions. And this together is one encoder layer. Now we have this entire one encoder layer, and oh sorry, now we have the decoder. In decoder we use similar multi-layer attention, but one thing extra we use is masked multi-layer attention. Why we use masked multi-layer attention? So that we don't see information from the future. We try to mask those informations, because sometimes, ideally this can have, like the input for this will be all the future words possible, but we shouldn't, right? If I'm translating a sentence, I should only know information of what all I translated till now, not all the words that can be translated in the future. So that's why we use mask multi attention. And other parts are the same, multi attention and feed forward. So this is my overall architecture. I have my encoder block, n encoder blocks, and then we send those to n decoder blocks, and finally you output the probabilities of each particular word. So you can just look at the zoomed in versions of what each multi-layer attention, and inside multi-layer attention what each scale dot product attention is. So if you have any doubts, maybe I can take. You can always look into the recorded lectures of this week if you felt that this is fast. So in this particular live session, I wanted to just cover all the topics so that you will know what all topics were there. And if you have any questions, you can ask for this particular thing. If you have any questions, you can ask. I'll just wait for a quick second. Okay. And then after that, we talked about 3D convolutions. So 3D convolutions for an RGB image, like if, for example, if talking about a video, right, that is a 3D. We need to do 3D convolution because you have a temporal dimension also. So this is one way to do 3D convolution, where each frame will have its corresponding RGB images. You can see the color representative. So each frame, there are three frames over here: frame one, frame two, frame three. We do your standard 2D convolutions, and then whatever outputs you get from those three frames, you combine them, and then you do one more convolution, which is your temporal convolution, and that will be your final output. So as you can see, this convolution basically you want you output four, and how is that forming? This is basically sitting on these three frames, and you get the output one, two, three, four. So in this way, we do a 3D convolution. I hope this is clear. Any questions? So this is not the only way possible. I think in recent times, I'm not very sure. There are papers which do a slightly different way, but you can see like this is a standard way to do a 3D convolution when you're given videos. And then we talked about generative networks, and we all know the difference between generative and discriminative. In one line to say, in generative, we understand the underlying distribution of the data, whereas in discriminative we don't really try to learn the distribution, we just explicitly learn the relation between the input output, whereas in generative we try to learn what is the distribution which is underlying the data. And this is a typical GAN architecture. So we assume that we have a latent space from which we sample the vector z. Usually it's a Gaussian sampling, it's a Gaussian distribution from which we sample z. Then we have a generator. So here, this generator basically it generates an image. So we use transpose convolution over here, because here we go from a smaller vector, smaller spatial dimension to a highest spatial dimension, and we generate a vector called g of z. Now we have the original sample, real sample, and we have the generated sample, and then we ask the discriminator to identify which is the real sample, which is a fake sample. So the goal over here is to fool this discriminator. So if you fool the discriminator, we can know, okay, then the generator is generating so realistic images that the discriminator can't identify which is real or which is fake. So that is the main goal of the GANs, where we try to generate images, and we trying to optimize the generator. We try to make it more and more realistic images, where at the same time we want to maximize the discriminator. That is, we want to fool the discriminator such that it can't identify which is a real image, which is a fake image. Since we have this maximization, minimization, so it's a min-max operator. When this is why it's called the adversarial learning, because it's a min-max operator optimization. Similarly, we have variational autoencoders. So in variational autoencoders, what we try to do, so here the difference is, in GANs, we're not really learning what the distribution form should be like. We're not learning with whether it's a Gaussian with so and so shift or anything. We're not learning the explicit distribution. We're learning the implicit. We know that there is a distribution, and we're just generating what the image should look like. Whereas in VAEs, we try to learn the explicit distribution, because this is what we're trying to learn. We're learning the mu and sigma along with some noise. Basically, we try to learn what the underlying distribution is, explicit distribution. So how we do that? We have your input X, we have your encoder network, which reduces the spatial dimension, and then you have your embedding layer, embedding distribution, which is parameterized by mu and sigma, and we add a small epsilon noise, and then we send this to the decoding network, and then we generate the original input X, which is your X bar, and we try to minimize the loss between X bar and X, because these both should be same ideally. So we try to reduce this difference between X bar and X. And so the loss function basically combines of your MSC and your KL divergence between these two distributions, encoding and decoding distributions, which is Q phi and P theta. We try to minimize the KL divergence between these two distributions along with the MSC loss. That is your total elbow loss for your variational autoencoders. So this is your standard variation autoencoders. And one thing is, since you are learning a explicit distribution, there can be some gaps inside VAEs. What I mean by that is, the distribution learned, it might not be a smooth manifold. There might be some masses accumulated in some parts of the manifold, some are completely empty. So that is why this is one problem for VAEs. Whereas in GANs, you learn a smooth manifold. So that's why people try to combine GANs and VAEs, and then they came up with something called as adversarial autoencoders. So you can always look into that part of the video lecture. I just skipped over here because it's a simple combination of VAEs and GANs. So if you understood these parts correctly, you just combine them, and your adversarial autoencoders is basically you create your adversarial autoencoders. Okay. And then finally, we talk about few shot learning. So in few shot learning, I think this is a relatively newer concept, like since last decade itself. So what we try to do is we want to learn the particular task in as few samples as possible. So that is the main objective of few shot learning. So if I'm given a neural network model and I want it to learn a task, what could be the task? Task could be like classify dogs, classify parrots or something. If I wanted to learn a task, I want it to do in as many small fewer samples as possible. Now, how do people basically train such neural networks? Is something called as they first create a data set which is called as meta training set and meta testing set. So as you can see, you have your meta training set. In each meta training set, you will have your own train set of that particular task along with its test set. So now imagine your original supervised classification, which used to have train and set. You can assume that to be your one particular what is it, a data set in your meta training. That will be one particular instance in your meta training where you will have your meta train set and your meta train test set. And so in this way, you're basically what you're trying to learn is you're trying to learn the task itself. You're not learning what this particular task is needed. You're learning how to learn a task. So that's why we call this the meta learning. What I mean by that is you're not fixing on your neural network to learn, okay, do this task, how to perform classification of dogs. We're not making it learn that. What we're making the neural network learn is how should I learn to classify anything, how to learn to classify anything if I get few samples at test. So that is my task over here. So you, it's a bigger task. I hope the difference is clear. You're meta learning something. You're meta learning how to perform the classification task irrespective of whatever the samples are, like whether it's a dog, parrot, or anything. So that is what meta training and so for that we divide into meta training and meta testing. And there are, yeah, do you have a question, Swati?
Yeah, so what is the difference in this metric learning and meta learning?
So good question. So that's what I was gonna say. So metric learning can be used as part of meta learning. So you can use metric learning to learn such things basically. So
Okay.
yeah, metric learning actually falls as one type of a few shot learning, and in few shot also there is different categories, non-meta and meta. So metric learning is a type of meta learning which can be used for few shot learning.
Okay, okay.
Okay. So in meta learning, basically there are three main methods: metric learning, optimization based methods, and model parameter based methods. So and then there are hybrid methods, which is basically combination of these methods. So in metric learning, like I already explained, basically you'll have to learn a similarity. You'll have a similarity loss function, and you want to learn the similarity network. There are many variations like Siamese network, prototypical networks, relational networks, so and so, so and so. You can always look, but all of them follow the same general idea or principle which we talked about, where you'll have input samples and you want to learn whether they're similar or dissimilar. And then there is something called as optimization. Yeah.
Is there any way to find out like which type of few shot learning to be used in what scenarios?
Uh, so all of them have their own advantages and disadvantages. So for example, model based methods are more what do you say, they are memory intensive. Like you'll have to learn an entire model parameter. It's harder that way. Whereas optimization based methods are lighter. So I don't think there's a golden rule which can easily say. I think you'll have to just try out for your task which is working.
Okay, and in earlier slide you said that you will be just giving images. Train and meta learning is train set and test set, and you so we will have only one pair in the testing set, and we will have the set of images in the training set. Is it? Sorry, one image testing set, and other images will be in the test training set. Is it?
No, no. So in meta train, what happens is like just focus on this block, the first block in meta train. Here
Okay.
in that block also we divide the data set which we have into two parts, your training part and your testing part. So they have the labels available with them. So don't worry about the labels. The labels are available with them. So here we do a normal classification where it learns on this training, and then we predict on what the test samples, and we find out what is the score. So then we keep on doing that for different types of data over here. So each data block will have its own set and own test set. So here we're learning how to do the task itself, if you understood.
Okay, okay. So it will have a sub data set. It is
Yeah,
not just data set, but samples of data sets, right? Pair of data sets.
yeah, in a way you can say.
Okay, and it will auto learn what task has to be done here. Is it?
Exactly.
So, can you just clarify that more? How it will, for example, whether it should do classification or whether it should be doing segmentation, or how it will explore on its own, like what task.
No, no, no. No, that task because you'll have labels with it, right? So each image will have its label. So if it's a just a bird, it's a classification task. Or if you have a label like a class and bounding box, it's a object detection task. So each of
Okay.
these images will have its corresponding label. That's how the task will be learned.
Based on the labels, it will auto
Exactly.
discover.
Yeah, yeah. So that is what the entire task is. Depending on your label, if it's just a class, it's a classification. If your label is class and bounding box, object detection. If your label is pixel wise classification, it's segmentation.
So maybe one set will have object detection, other will have segmentation.
No, no, you can't do that. All of them should learn. All of them should learn be only classification. Here, the task you can do that also, but that's a bit more complicated. There's something called as continual learning and everything. That's a bit more complicated. But at least for now, you can assume that the classes, the tasks are same basically, but the classes are different. So it's all image classification task, but this is with data 1, this is with respect to data set 2, this is with respect to data set 3, and in future we'll get some unseen data set itself. The classes will be different, like you can see the in future you'll get dog classes, whereas you'll never see dog classes in training. But since we are learning meta learning model, right, just given the dog classes also, we can immediately learn the classification, and we can say we can test with the query set that these are all dog classes.
Okay, okay.
So this is not multitask learning in a way. It's not like you can learn different tasks at a time. That is also possible, but it's a bit more complex. But for now, you just assume that the data sets are different over here. And what we're trying to learn is if you get a data set which is completely unseen during training, but you have a certain set of training samples, few samples, you can quickly learn to identify what the task is, classification task, and you can predict on the query set. Okay, and these are the classifications. Yeah, and then we talked about self-supervised learning, and I think in self-supervised learning, there what we try to do is we have all the input images, and what we try to do is we try to learn good representations of the input data set. We don't worry about what the labels are for right now. We don't worry what the task is also right now. In self-supervised, you can think of it as a pre-training stage where you just learn good representations of my data, and once you learn those representations, you'll use them to do whatever task you want. So self-supervised learning is like a pre-training step, and usually these are the standard self-supervised learning tasks, a pretext task we call them. These are the standard self-supervising pretext tasks which people use. The first one is called the image in painting. The task is simple. You have your input image, but we create a small mask, and basically we cut off this mask and we send this as to the encoder. And what we try to do is we basically tell the encoder, we tell the neural network to fill in this gap. And since we have the ground truth, which is basically the cutout part, we only cut out, right? So we'll have the ground truth. So we'll know what it should actually look like. So in this way, we are making the neural network learn good features by filling in the gaps of the image. So this is one task, pretext task. Another pretest task is jigsaw puzzle, where we try to arrange the patches of the image. We'll try to arrange the patches of the image such that it forms the original image. Like the tiger, if you create patches and like randomly permutate it, you get this bee. What we want the neural network to do is we want it to arrange all these permuted blocks such that you look it like it look like the original tiger image. So as discussed, what we do is we create a permutation set where you have a particular index, and that index corresponds to a particular permutation combination which you've done, and we send all those patches, whatever patches we create, as input, and each of them combined all together predicts a index number. Okay, this is 64, means whatever input we got, that is corresponding to the index 64. So this is the jigsaw puzzle pretext task. And then again, after that, we have the rotation prediction task, where you have your original image, and what we are trying to do is we rotate it at different degrees, and we send this as the input to the neural network, and we try to predict how much degree is it rotated, what degree of rotation is it. Is it class 0, which is 0 degrees, or class 1, which is 90 degrees, or so and so. So based on this is more stronger because we are trying to look we are trying to make the neural network look at objects present in this image and uh, uh, predict the orientations of those objects. So in this way, you can also create your own pretext task as long as it is general and the representations learned from them can be used for many tasks, computer vision tasks. And then finally, we talked about adversarial robustness, and what we wanted was key. We want to make a model very robust as possible, and we talked about first create adversarial examples so that based on those examples we can identify how or where the model is weak, and we can basically then improve the robustness. So to first create adversarial examples also, you have certain techniques, so you can see what the techniques are. They're classified into these categories. White box attacks are basically where you have access to your model parameters, and in black box attacks you have no access to your model parameters. In untargeted attacks, you just want to make the adversarial image such that it can misclassify that particular image. And then after in targeted attacks, we want to make the adversarial example in such a way that it not just misclassifies, but it also misclassifies into a particular target class. So that is the difference between untargeted and targeted attacks. And the technique which we saw to create adversarial examples is FGSM, which is a standard and good technique. So here FGSM basically takes the original input and it adds some, you can say epsilon is some constant value. It adds some constant value to the gradient of the loss function which you get. So based on this, you now create adversarial example which can fool the neural network. And if you want to do a targeted attack, you can just subtract it with that particular loss function corresponding to that target which you want. So in this way, we'll create adversarial examples where the neural network will always classify into the target class which it want to do. So the target class is not the right class. You have to remember that. So here we are creating examples so that we fool the neural network into misclassifying that particular example. So yeah, so these were all the concepts which Sir thought. So maybe now I can just all the things which I wanted to talk about. Maybe if you have any questions, we can take up now. So from my end, this is what I wanted to explain. If you have no questions, you can leave. Thank you for joining. But I'll be staying over here for any questions.
Yeah, Avin, can you please share any contact details?
Sure.
Yeah.
Yeah, I've shared my email address.
Okay. Yeah. Thank you. I will just wait a second. And do you have any reference material apart from these PPTs?
Reference material, I don't think. See, because most of these fields are coming up very new, so there are no books as such. You can refer to books, but better than that, I would suggest reading of the blogs which write explanations about the research papers. So those actually help you a lot. So if you take any paper, you just type the paper name, and after that you type explanation. You'll get these Medium blogs, analytics with their different blogs basically. So they explain the papers well. I don't know if there is any one book which talks about these all new techniques.
What about
Hello.
ChatGPT?
Sorry,
Yes.
just a second, Saroj, 1 second. Let her complete a question, then you can ask. Yes, Swati, you can go ahead.
No, would you like to suggest anything using ChatGPT if I want to learn this very faster? There are several tools.
Yeah, I
You can-
think uh, I haven't personally come across this, but I think in general, just the ChatGPT website, right? It's updated, and you can definitely learn a lot of things. At least for contents where you feel uncomfortable, or you have specific questions and you don't have time to ask anyone. I think ChatGPT is more or less accurate in that, the website ChatGPT. Apart from that,
Okay.
specific tools, I'm not really sure. I haven't come across any specific tools. But more or less, I think as far as I've heard, ChatGPT understanding of these methods and models are more or less good. Unless it's very recent model or something. If it's an old model, it should be good.
But the results we have to validate, right? Those may not be correct ones.
Yeah, so that's one problem. So I don't think you have any solution for that. So uh, I don't think.
Only we can just validate whether that is correct response.
Exactly. So that's what I'm saying. You can't ask very specific doubts also, then it might be wrong. But overall, if you have, like, for example, if you ask it concepts like what convolution does or where to use transpose convolutions, it can answer because those are general and generic and popular techniques. But if you have very specific, like
Scenario
why,
based, if I give some scenario and ask.
yeah, like for example, why the negative sign in targeted FGSM, I don't think that it can answer.
Okay.
I mean, it might. I'm not really sure. I haven't tried, but something specific like that.
Yeah, still there are some limitations.
Yeah.
Hello, sir.
Yeah. So
Can can you suggest any like you suggested the blogs because for the assignments and in the depth how the numerical easily can be solved for the deep learning. So can you suggest from your side because your explanation we felt as good. So can you suggest from your side ki some book or some links that will be helpful for this exam also?
So as far as I remember, I don't think you have a programming exam. I'm not sure. Do you have a programming exam also?
Uh, no, sir, but programming, based on the programming, they that will be because
Okay.
while giving the assignment, they have given the programming as well as the numerical in the deep learning. Means that questions, all questions were not theoretical.
Okay. So to learn for the programming assignments, PyTorch official tutorials are the best, I would suggest, because I haven't seen any other tutorial which is as complete and
Yes,
good at
sir.
explanation. So if
Yes,
you
sir, but
Hmm.
numerical for numerical, sir. For for a deep learning, whatever numerical based questions are there in the quiz they have given.
Okay. I
There are two
for
categories, no, sir.
that for that I'm
Because
also
sir has explained the theory, but the questions that were there in the assignment. So from that transcript, because book also sir has mentioned, but that is book is nothing but a sir's explanation as a transcript.
No, but there is another book which Sir refers, right? In after each lecture, Sir asks us to read certain books. Each of those books will have exercise problems. Have you seen those?
Uh, sir, not means explanatory stuff I want, sir. Good explanatory stuff. Because going through all the books and that means like
I
some
don't. I
according to you.
I don't think in that case. I'm also not sure if there is anything like that. So one option for the numerical problems which you face in assignments or anything, you can always refer to the exercise problems which Sir suggests the books, right? Usually, if you look into the books, the chapters, the behind end of the chapters, you'll have some exercise problems. So that is one way to learn. Or another way to learn for numericals is, again, you'll have plenty of these analytic vidyas and all these websites where you have a lot of numericals, but those might sometimes not be of very good standard also, but that will actually help you also. You can look into those. Apart from that, only book, like you want basically only book which talks about questions, numerical questions and their explanations. I don't.
In in the live sessions of machine learning for NPTEL courses only, they have in the live sessions they have explained, sir. how the numerical questions of that sort of can be solved.
Okay.
But here there is some problem, sir. So that's
So
why I
here
have asked.
in this course we explained the programming assignments mostly. So
Yes, sir.
in every live session we talked about the code walkthroughs and
Yes,
how to
sir.
do the coding.
Yes, yes, sir.
So
That's why I asked.
did you get any explanations from the NPTEL answers like after you submit?
So, some yes, one or two lines are there, but like thoroughly